Hello learners, welcome to Education Online program. I'm teacher Willa Lucia. So in our previous lesson, we looked at the Newton's laws of motion. We stated the first Newton's law of motion, which says that a body continues in its state of rest or uniform motion unless acted upon by an external force. Then we also went ahead and looked at the second Newton's law of motion, which states that the rate of change of momentum is directly proportional to the force applied and takes place in the direction of the force. Where we say that when you try to push something, so as you're pushing it, let me give an example. Like you're here. I assume this is you. So you're trying to push a wheelbarrow. This is the hand of our wheelbarrow here. This is our wheelbarrow. So as you're pushing it there is a force you are applying, and the force is in that direction. So this one keeps, it accelerates, because if you're pushing it, that means it's going to leave that position. So if it is moving, it takes this direction where you're also applying the force. So if this is our acceleration, and then this is the force we are applying, there is a mass of, this thing has got a mass, the wheelbarrow. So meaning that if we talk of the momentum, we know that we're talking about the mass and the velocity with which the body is moving. So you'll see that this one, the mass takes, it moves, the whole mass of this, and the velocity will take the direction of the force you applying on the object. So today we shall be looking at the third Newton's law of motion. So let's have it here as our third. The third Newton's law. The third law, let me just put it as the third law. In your previous lessons, we looked at force. So we saw very many things under force, and there are two types of force where we talked about the contact forces and the non-contact forces. What happens is that with the contact, the force between the thing involves direct contact of the two objects. But then with the non-contact, you see that it does not represent the direct contact, but then the force is transmitted through the space between the two objects. So you'll see that if it is transmitted between the two, we talked of so many forces under that, where we have the gravity, we have the electrostatic forces. So now, take example of two objects here. If you have your A and then B, these are two materials, or we can say two objects. So we are going to make them touch each other. Let's see what happens. If 2 is directly put on this, because if you put it like this, that means that there is a space you're already creating between the two. But then at this point here, if you either bring A just close to this, to B, we have our A, and then the B is also at that point. Here we are saying there is a direct contact between the two. So if there is a direct contact between the two, you'll see that this A here has a force it is also exerting on the B, and the B has a force that it is exerting on the A. So what are these forces? So you see that Newton's, when he tried to discover this, he said that these two forces are known as the reaction and the action, meaning that if when one object exerts, when one object acts on another, that other object is going to to react back to that action provided onto it by the object. So this here gives us the third Newton's law of motion, where we state it as wherever there is any action, there will be an equal and then but opposite reaction. Meaning, whenever you apply any action on an object, that object is obviously going to react back. Sometimes you don't feel that. If you don't feel the reaction, but it is still there. For instance, if you sit on a chair, what happens? As you're on your chair, let's take this as our chair. This is our chair, and here you are sitting on this chair. You see that there is direct contact between you and the chair. There is a force you're exerting on this chair. So what is this force you're exerting on the chair? The force here you're exerting is the weight, because the moment you sit on it, that means that your whole weight is put on the chair. So what happens is that this chair is going to react back. So if it is reacting, the force it is going to exert on you is not also going to be downwards. It is going to react on you, but then in the opposite direction. So you see that the reaction the chair is going to produce will be equal to your weight. That's why you see that you sit on the chair and the chair does not break, because the two forces are balanced. So we can say that our third Newton's law states that for every action there is equal but opposite reaction. So this is how we get our third Newton's law of motion. So you see that there are so many common examples that explains Newton's law of motion. For example, let's take that someone is on the boat. So this is our boat, and then the person is right here. When you reach with your boat to the shores of the river or the lake, you want to get out of the boat. What happens? You'll see that when this is like our water, this is the water. When you try jumping out of this boat, there is a force. There is an action you're taking. So that means that there is a force you're exerting on this boat. But then if you exert the force on the boat, what happens? Does the boat also react back, or it doesn't? Our boat actually does react back. How does it react? You see that when you jump out, so as you're jumping out here, you're leaving the surface of you're leaving the boat, you're already somewhere here. You see that there is no contact there. So the moment you are jumping, there is a force you already acted on this boat, and this boat is going to react back. How will you see the reaction of this boat? It will react in such a way that the boat will try to get back into move backwards. So that is the kind of reaction that explains the third Newton's law of motion. Not only that, let's take example of a lift. So these are examples. we've talked about a man jumping off a boat. So let's take a look at a lift. How does this third Newton's law of motion apply to a lift? You'll see that when you're in the lift, what happens is, assuming this is you here, and this is the lift. Okay, this is our lift right here. You're standing on the lift, inside the lift. So you'll see that when you're standing just and the lift is not moving, there is a force you're exerting on the lift. Remember, there is direct contact between your foot and the floor of the lift. So you'll see that you're going to exert your whole weight on the lift here. This is our weight, because our weight is equal to the mass and the acceleration due to gravity. So if this is it, what happens with the lift? The lift is going to oppose this weight by producing a reaction which is equal to your weight. So that reaction it will produce goes in the opposite direction, and this is known as the normal reaction, and it is given letter R, which is the same as normal reaction. If that is the case, what happens to the acceleration? Because remember, a lift moves. It can go upwards or downwards. But then in this case, when you're just standing in the lift, these are the two forces that will act on the lift. And at this point here, the acceleration is equals to 0. Why is the acceleration equals to 0? Because here the body is maintaining a uniform velocity, and when the body is maintaining a uniform velocity, is much less like the body is not moving, it is just at rest. So if it is at rest, that means our acceleration is equals to 0. So take a look at this. What if now you press the button and you want the lift to move? Let us take the upward motion. Here you were just standing. Now, what if you've started accelerating but moving in the upward direction? What happens? You'll see that in the lift there will be 3 forces acting in the lift. What will be those forces? We shall have, let's first have our lift there. And this is you here. So your weight is still there, which is mg. And then we say that the lift is going to react in the opposite direction to give us the normal reaction. So what is going to be the third force there? The third force is going to be the accelerating force. So where is the accelerating force? Since we say that our lift is moving upwards, that means the accelerating force will be taking the upward direction right there. So here is going to be the accelerating force. So if you have it like that, let's see what happens. Are you going to feel heavier in this lift, or you're going to be feeling lighter? Because you know that there is this weight you're applying and then of that reaction. So when these two forces are there, and even you have the third one including the accelerating force, what happens to your weight? Let's see. You see that when this one is moving upwards, the normal reaction is also acting in the upward direction, we are going to have our reaction, our accelerating force here. The accelerating force, which is ma, that is from the second Newton's law of motion, where we proved that our accelerating force will be equals to the mass of the body and the acceleration, the rate at which the body is accelerating. So that's why we're taking it there as ma to be our accelerating force. So the accelerating force here will be equals to the reaction that the body is that the lift is offering to your body, which is r. But then what of the weight? We are going to subtract the weight. We are subtracting our weight from the normal reaction. Why? Because if you want to find the resultant of two forces acting parallel to each other, what do? You subtract, because they are acting in the opposite direction. So if you subtract it like that, let's try to make the normal reaction the subject, and we see how much reaction the lift is offering. You'll see that when you have your ma at the accelerating force, which is equals to the normal reaction minus the weight, we are making our r at the subject by adding the weight on both sides. So we shall have our ma plus mg, which will be equals to our r minus mg plus mg. We are adding it on both sides so that we want to cancel it from this side to take it here. You'll see that our normal reaction will give us the accelerating force plus the weight. So let's factorize our mass. So we shall have the normal reaction equaling to the mass, and then the acceleration due to gravity. Now take a look at that. You see that when the lift is moving upwards, that reaction it is providing is going to be greater than the weight you are actually exerting on the lift. So if your weight is less than the normal reaction, what happens? It means that when the lift is going to start, you're going to feel heavier, because our normal reaction there is going to add the acceleration, the accelerating force, and then it will add onto your weight. So now you see they have added something, topping something on your weight. So as it is moving upwards, you're going to be feeling heavier. So that will explain a question when they tell you to explain why a person feels heavier as the lift is moving upwards. So you don't have to look very far, but then come to check the Newton's law of motion. So you can use the Newton's law of motion to explain such. So if it is like this, if they are saying that a person will feel heavier as the lift is starting to move upwards, what if now the lift is up and then it has to come downwards? What will happen? Let's take a look at that. So this time round, our lift is coming back downwards. So this is the lift. And then you're here. So you're moving downwards. What could be the forces that will be acting on the lift? So there are still 3 forces that will be acting there. That is your weight. Obviously, when you exert your weight on the lift, it is going to react back. So if it is reacting back, meaning that we have the normal reaction also acting there as a force. What else do we have? We say that it is the downward motion. That means that our lift is going to be moving. So we are having also the accelerating force. When it is coming down, it has three forces, just the same way when it is going upwards. But then how are these forces behaving? What direction will they be taking? So we know that here you're going to be exerting your weight, which is obviously going to be to the earth, to the center of the earth, because we say that weight is taking the mass and then the acceleration due to gravity. So if we have it like that, since your weight is there, there will be an opposing force but equal to your weight, which is the normal reaction, taking it upwards. So here is our normal reaction R. Now what is the third force? That is the accelerating force. How will the accelerating force be? You see that it is coming downwards. That means that it is accelerating downwards. Our arrow will be taking this direction here, down. So now if it is moving downwards like that, how would you get the value of this reaction offered by the lift? So you'll see that, let's consider the accelerating force. So if we have an accelerating force, will be equals to, we are having the weight. So we shall have our weight here, but then we are subtracting the normal reaction. Why are we subtracting the normal reaction? We are subtracting the normal reaction because if you look at, so this is the person right here. We are saying, okay, if we have this, let me draw a Cartesian plane. We have this taking that direction, and then we have maybe and that. So you see that when you have any force going this side, assuming this is F1, and we have another force acting downwards, but on the same here, that is F2. So you see that our arrows are facing differently. So you shall take one of the forces and subtract the other one from it. So you will see that you will have either F1. I have taken F1 because if you look at this, it's taking the positive, and then this side here downwards will be taking it's taking the negative. So I will take our F1 minus the F2. That is why we are subtracting this a normal reaction from the weight. So if we subtract it like that, what is the value of this accelerating force? You find that accelerating force is equals to ma. So if it is ma, what is our weight? The weight of this body, the weight you're exerting is mg, your mass, and the acceleration due to gravity acting on the lift, minus the normal reaction, which we have it as r. But in this case, we want to make our normal reaction we want to make our normal reaction the subject. So what do? We are going to bring we can either bring this here, or we bring the normal reaction first, either of the two. So we shall have our ma minus mg is equals to negative r. So what will happen here if it is minus that? If you try to factorize your m out, you'll be left with a minus g, but equals to what? Negative r. We do not want the coefficient of r to be negative, but we want it positive. How shall we make it positive? We can make it positive by dividing through by the negative value, which is -1, the coefficient of the normal reaction. So we shall have it here as dividing it by -1 and then dividing it here by -1. So that means we shall, this negative and that will give you a positive. So we shall have our m minus g divided by -1 and then plus, it is not a plus, but then equals to r. If it is equaling to r, we don't have to leave our equation with a negative down here. But then you see that this negative you can divide through by this negative, each number here. So if you're dividing it by negative, what will happen is that you'll see, if you divide this by negative, we shall have m negative a, but then negative divided by negative will give us plus g, which is equals to r. That means that our r is equivalent to the mass of the body, and then our acceleration due to gravity minus the acceleration with which the body is moving. So you see that if you have this, take a look at this, and then this equation here, these two, what is the difference? You will see that the normal reaction offered by the lift on the person is much less in this point here when the lift is moving downwards. But then if you come to this point here, when it is going upwards, the normal reaction is greater than the weight, meaning that as the lift is coming downwards, the reaction offered by the lift on the person in the lift is less than the person's weight, because you see that for you to get the normal reaction here is going to be equivalent to only the weight of the person minus the accelerating force. So when you subtract the accelerating force and then yet here you add the accelerating force, the person is going to feel much lighter. So as the lift is coming down, this is why you feel light, because the reaction offered by the lift only gives you the weight, and then subtracts the force at which the lift is accelerating downwards. So these are some of the explanations if you want to use the Newton's third law of motion, which says that the reaction is equals to the action. So for every action you take, there will always be an opposite but equal reaction. That's why most of the times we do not feel the kind of reaction that is on us, because that reaction is almost the same as the weight we offer. So if your weight is equals to 10 and you sit on the chair, that means that the chair is going to offer a reaction which is equal to also 10. So that is what we have today about the Newton's third law of motion. So we should always know those three laws. We should know which one comes first, which one is the second, which one is the third. So if you know how to define all, we should also be knowing how we get the accelerating force, which Newton's law of motion gives us accelerating force. We saw in our previous lesson that it is the second Newton's law of motion. So with that, we come to the end of our lesson for today. We shall meet again in the next lesson.